Hello, I'm J.D. Harrington, Public Affairs Officer for NASA's Science Mission Directorate from Washington, D.C. and headquarters. I'd like to welcome you today to the Mission Science Briefing, where we'll discuss the planning for NASA's newest spacecraft, the Wide Field Infrared Survey Explorer, otherwise known as WISE. As for the order of events this afternoon, we have 4 panelists joining us this afternoon. Each will give a short briefing, and then we'll open up the question and answer session. I'd like to take a moment to welcome and introduce our panelists. To my left, your immediate right, we have Ted Wright, the WISE Principal Investigator from UCLA. Next to Ned, we have Amy Meinzer, the WISE Deputy Project Scientist from the Jet Propulsion Laboratory in California. Next to Amy, Peter Eisenhart, the WISE Project Scientist, also from JPL. And next to Peter, John Elwell, the Project Manager for the WISE Science Instrument for the Space Dynamics Laboratory in Logan, Utah. And with that, I'd like to hand off to the discussion to our first briefer, Ned.
Thank you, J.D. WISE will survey the entire sky with much greater angular resolution and sensitivity than previous missions. This means that WISE will see much fainter objects and provide much sharper images. As a result, WISE will see hundreds of millions of objects, and of these, millions will have never been seen before. If I could have the animation, the first animation, it will show how WISE is going to survey the whole sky. You'll see WISE orbiting around the Earth over the line between day and night. And as it orbits, it maps out a strip of sky. Now, as the Earth goes around the Sun, the strip of sky being mapped shifts over until after 6 months, we've covered the entire sky in the infrared, giving us an entirely new view of the universe. Now, infrared waves are longer than visible light. In fact, the bands that WISE is observing are 5 to 33 times longer than red light that your eye can see. As a result, WISE is good for looking at sources of light that are cooler than the sun and light bulb filaments that provide the optical light that we actually look at. Now, any object that's warmer than absolute zero radiates infrared, and that includes objects at room temperature. So if you get the next image. Yes, this is a picture of me in the infrared. And you can see what's happening here. Where my skin is warmest near my eyes, it's glowing the brightest. And where my clothes are blocking, holding the heat of my body in, the image is coolest. So what we see are things that are hot are brighter than things that are cool in the infrared. So previous missions, going back 26 plus years, have mapped the entire sky in the infrared already. But let's take a picture, look at the whole sky image that we have now. That's on the next slide. If we look at this slide, we can see the very thin plane of the Milky Way and right into the galactic center. This is very significant because normally in optical light you can't see it at all. And the reason this happens is that infrared light can easily penetrate the interstellar dust that normally blocks our view of the center of our galaxy. And in fact, we can see radiation from this dust, especially in regions where new stars are forming now. But if we zoom into the galactic center on the next image, okay, here's the galactic center as seen by that mission that was launched 26 years ago. It only had 62 pixels in its camera, and as a result, this image of the galactic center is fairly blurry. But if we replace that with cameras with more pixels, we go to the next slide, and this is what WISE will be able to do over the whole sky. Okay, because WISE has 4 million pixels, it's going to provide this much improved, much sharper image where you can see a tremendous number of sources over the whole sky. So far, only a few % of the sky has been mapped with this kind of resolution. So WISE will provide a roadmap. Now, this roadmap will be used by bigger telescopes like Hubble, Keck, the James Webb Space Telescope, SOFIA, in order to study interesting objects. So WISE is going to provide a wide-angle view. It's like the wide-angle lens on a camera, whereas these large telescopes are like telephoto lenses on a camera. and you use them to provide detailed images in zoomed-in small areas on the sky. So WISE is taking a 4-color image every 11 seconds. This is very fast for a space astronomy mission. And as a result, WISE will take millions of images over the mission. We will stitch these together to give a panoramic view of the whole sky. And on this view, we're going to see many interesting asteroids, stars, and galaxies. But I'm sure that the most interesting things that we actually see are going to be total surprises because we just haven't looked at this volume of the universe before. Now, I've worked on WISE for 12 years, and it's been a long haul, and it's almost ready to launch. But what I'm looking forward to this year for Christmas is WISE data. Now I'll pass it over to Amy Meinzer, the Deputy Project Scientist, who's going to tell us about the interesting asteroids that WISE will see.
Well, thanks a lot, Ned. So it's really great to get to be here finally to tell you all about WISE. We're so close to launch now, and it's tremendously exciting. And as Ned mentioned, WISE is an all-sky infrared survey. So you can kind of think of it as the GPS map to the universe in the infrared. And as such, it's going to show us things that are some of the most distant objects in the universe, like faraway galaxies. But it'll also teach us a lot about our Earth's very nearest neighbors, the asteroids and the comets. So I have an animation here that shows that most asteroids in our solar system reside in the main asteroid belt, and that's between Mars and Jupiter. And you can see those as the blue dots, or the bluish-greenish dots in the animation. But some asteroids have orbits that take them close to the Earth's orbit, and we call these the near-Earth objects. Of course, they have some potential to collide with the Earth, so we would like to learn more about this population of near-Earth objects. Now, we expect that WISE will discover about 100,000 new asteroids in the main asteroid belt and several hundred new near-Earth objects. So it should teach us a lot about the asteroid population. Now, as Ned mentioned, anything that's warmer than about absolute zero emits some amount of infrared light. And in fact, I'm pouring out infrared light as I sit here. So since asteroids are about the same distance from the sun, the near-Earth objects anyway, as the Earth, we expect them to be about room temperature. And that means they're going to glow very brightly in infrared light. Now, I have a set of 4 sample images from another NASA infrared telescope called the Spitzer Space Telescope. And this is going to show you how infrared is a powerful tool for finding new asteroids and for characterizing them. If I could have the next animation, you can see these 4 frames of data. And the reason the asteroid appears to jump back is because they're looped. But basically what you're seeing is that the asteroid is a very red dot. That's because it's glowing very brightly in the infrared. And it's moving, which makes it easy to distinguish from the other stars and galaxies in the image. So WISE is going to be a very powerful tool for finding new asteroids. Now, the Spitzer Space Telescope is only able to survey about 1% of the entire sky in detail. As Ned mentioned, it's like a telephoto zoom lens. So it's very good at getting detail on specific objects. But if you really want to find a lot of new asteroids and comets, you need to look over a much larger area of the sky, and that's what WISE is going to do. So, as I mentioned, infrared is a very good way of not only just finding the asteroids, but also characterizing them, learning more about them. I have here a couple of rocks, and one of these rocks here, as you can see, is small but very shiny, and the other one here is larger, but it's dark. Now, if these 2 rocks were floating in space and we could look at them with a visible light telescope, these 2 rocks would look about the same size, and that's because the small shiny one is going to reflect about as much sunlight as this big dark one. However, with an infrared telescope, we're actually able to see the heat that's being directly emitted from these 2 objects. So the big dark object is going to emit more infrared light, and it will appear brighter to an infrared telescope. So this means we get a more accurate measurement of the object's true size with the infrared telescope than we do with a visible telescope. So in addition to just measuring their sizes, we can also use the infrared data to learn more about the asteroids' compositions. We'd like to know whether or not the asteroids are, on average, soft and squishy like a marshmallow or hard and dense like a piece of solid metal. And that's an important thing to know if we are to someday plan a future mitigation campaign in the unlikely event that we do discover an asteroid that's on a collision course with the Earth. So WISE will teach us a great deal about the asteroid population. So we may not have Bruce Willis on our science team, going around blowing up asteroids, but WISE will teach us about how many there are, how many are dark versus how many are bright, how big they are, what their sizes are, and what they're made out of. And with that, I'm going to hand it over to our project scientist, Peter Eisenhart, who's going to tell us about some of the other great science WISE will do.
Thanks, Amy. So as we've been saying, WISE is going to observe everything in the universe that is further away from the sun than the Earth is. Amy's just told you about some of the closest objects, asteroids that come near to the Earth. I'll be telling you, moving beyond the solar system and telling you about some of the superlative objects that we'll find in the rest of the universe, including the nearest stars and the most luminous galaxies. Now in the next graphic, we see some stars here, our sun in the upper left, and then a lower mass star. And you can see that it's cooler, and therefore it's putting out more of its radiation in the infrared. As we go to lower and lower masses, we get to about 8% of the mass of the sun, or equivalently about 80 times the mass of Jupiter, stars can't sustain fusion anymore. That's the nuclear fusion reaction that keeps the sun hot. And so over billions of years, these failed stars, or brown dwarfs, will cool off until they become invisible at optical wavelengths, but they remain bright in the infrared that WISE will observe. Now in the next graphic, we're looking at the known stars within about 25 light years of the sun. This is an artist's visualization, but these are all the stars that we know about within 25 light years of the sun. It's right down in the middle there. You can see that some of them are bright, but quite a number of them are faint. Now, we know from other studies that there should be about as many failed stars or brown dwarfs as there are ordinary stars, but among these 100 or so nearby neighbors within 25 light years, only a handful of those are actually brown dwarfs. And there should be about equal numbers of brown dwarfs and ordinary stars. So there should be something like 100 brown dwarfs in this volume of space. We don't know where they are because they're too cool to emit in the optical light that we're studying. What we have to do is look in the infrared, and we have to look everywhere. That's shown in the next graphic. That's exactly what WISE will do. We're going to find these nearby cool brown dwarfs and transform our view of the solar neighborhood. Now there's even a chance, pretty good chance, about 50-50, that one of these nearby brown dwarfs might be closer to the sun than any star that we now know of. The closest star that we know of now is called Proxima Centauri. It's about 4 light years away, and there could be a brown dwarf that's even closer. There's also evidence that brown dwarfs host planetary systems, just like our sun does, and that's the type of observation that will be possible with a follow-up observation, such as with the James Webb Space Telescope. And so there's a chance that the next planetary system beyond our own solar system that's visited by humanity will be around a brown dwarf that is discovered by WISE. Well, I'm now going to leap far beyond the solar system. I'm going to move not 10 light years away, not hundreds of light years away, where we expect to see star-forming regions or forming planetary systems, or tens of thousands of light years away, where we'll be mapping out the structure of our own Milky Way galaxy. I'm going to leave our galaxy behind entirely, go millions of light years away, as shown in the next graphic. Here's an example of a relatively nearby galaxy, some millions of light years away. It's called the Cigar Galaxy, or astronomers call it Messier 82. On the left, you see a visible light image. It looks relatively normal, a little bit disturbed. There's a dust lane running across the middle. But when you look in the infrared, in the Spitzer picture shown on the right, you can see that something truly dramatic and unusual is going on here. And what's going on is that this galaxy is churning out new stars 10 times higher, at a rate 10 times higher than our entire Milky Way galaxy, even though this galaxy is actually quite a bit smaller than our own Milky Way galaxy. There's a lot of dust associated with that star formation process, and it gets heated up and starts glowing in the infrared, and that's why we see that dramatic infrared picture. Well, our predecessor survey, the Infrared Astronomical Satellite, discovered that there's an even more extreme class of galaxies called ultraluminous infrared galaxies. These have over 1 trillion times the luminosity of the sun, most of it coming out in the infrared, and they're forming stars at a rate dozens of times higher than the Cigar Galaxy we were just looking at, maybe even hundreds of times higher. Now, studies with Spitzer have shown that galaxies like that are rare today, but they were common 10 billion years ago when the universe was 3 or 4 times younger than it is today. WISE has the sensitivity, we're designed to have the sensitivity to see these dusty, cataclysmically forming galaxies out to a distance of 10 billion light years or even more. And so we're going to find the most super duper hyper ultra luminous infrared forming galaxies in the entire universe, and we'll see just how extreme this galaxy formation process can get. Well, I've told you about some of the extreme examples that WISE is going to observe, and of course we'll observe everything in between these nearby stars and brown dwarfs. But one of the most exciting aspects of WISE, the thing that really gives it tremendous longevity, is that you can keep coming back to it. If there's some object that we discover years later, after the survey is long gone, that survey will still be there to go back to and see what the infrared properties of that new object were like. Today, 26 years after the Infrared Astronomical Satellite Survey, there's still hundreds of papers being written every year, hundreds of new papers that refer to that Infrared Astronomical Satellite Survey. And that's why we like to say that the legacy of all sky surveys will endure for decades. And now to tell you a little bit more about the instrument that's going to carry out this super duper survey, here's John Elwell from the Space Dynamics Lab.
Thanks, Peter. Now that you've heard about all the super duper objects that the astronomers hope to discover with the images from WISE, I'd like to tell you a little bit about the WISE instrument itself. WISE was built over the last 5 years at the Space Dynamics Laboratory of Utah State University in Logan, Utah. But as with any complex instrument, it requires input from many organizations across the country, including starting with JPL, our customer, and I'll point out a few of those organizations as I go through. The first graphic is a photo of the WISE instrument at SDL. WISE is basically a digital camera, just like one you'd buy and put in your purse or your pocket. A little bit larger, though. It's about 6 feet tall, it's 5 feet in diameter, and the instrument weighs about 800 pounds. So why do we need an 800-pound camera to take digital pictures of the sky? There are two primary reasons that WISE is so large. The first is that we want to take pictures of very faint, faraway objects, as the astronomers have described. And to do that, we have to collect a lot of light. If we move to the next graphic, you can see what WISE looks like on the inside. You can see pointed out in the drawing at the center of WISE is a telescope. This telescope was manufactured by L3SSG in Boston, Massachusetts. The telescope collects the faint light from space and focuses it onto our cameras, which we call detectors. There are 4 detectors in WISE. You can see those pointed out in the drawing near the bottom. And the detectors were made in California by DRS Technologies. They receive the light gathered by the telescope, and each detector looks at a different color light. But all the different colors of light that detectors look at is infrared light, or heat. That brings us to the second reason that WISE is so large. Because WISE takes pictures of infrared light or heat, we have to keep the telescope and the detectors themselves very cold. Otherwise, all we would see is our own heat, sort of like going out in the middle of the night to look at the stars and shining a bright flashlight in your own eyes. To keep the optics cold, we put WISE into a giant thermos bottle called a cryostat, which you can see also pointed out in the drawing. The cryostat was manufactured in California by Lockheed Martin Advanced Technology Center. The cryostat keeps the heat from the sun and earth off the WISE instrument, and it lets us keep the inside cold. But to get cold in the first place, we need some ice cubes. And for WISE, our ice is stored in some donut-shaped tanks inside the cryostat. The dark blue donut around the detectors near the bottom is one of those tanks. Now, we don't use water ice to cool WISE because it isn't cold enough. We fill the tanks with hydrogen ice or solid hydrogen, which turns out to be a great ice cube for us. It freezes at about the right temperature, minus 430 degrees Fahrenheit, and it takes a lot of heat to melt hydrogen ice, so our ice cubes last a long time. They'll keep us cold for about 10 months on orbit. The next slide shows a view of the completed WISE instrument from the point of view of a star. You can see into the instrument, and you can see the gold circle in the center is the first mirror of the telescope. There's about another dozen mirrors after it to focus the light onto our detectors. Although hydrogen ice is a great way to keep WISE cold on orbit, it requires a lot of effort on the ground to fill the tanks with hydrogen and to freeze them. The next graphic shows one of our technicians in the process of filling WISE with hydrogen. It takes us about 3 weeks to slowly fill the tanks. Can we move to the next graphic, please? Thank you. It takes about 3 weeks to fill those tanks and freeze the hydrogen and to prepare the instrument for flight. This photo was taken shortly before we moved WISE out to the launch pad and put it on the rocket. So in summary, WISE is basically a large digital camera which will take pictures of the sky in infrared light for the astronomical community. it's been a very exciting project to be part of. And with that, I'll hand it back to JD.
Thank you, John. We're now open to the question and answer session. If you would, as a reminder, please wait until we get the microphone to you. Start by identifying yourself and your media affiliation. And if you would, direct your question to a specific panelist to avoid any confusion. We ask that you remain seated and refrain from leaving the room until the conference actually ends. With that, do we have any questions here in the audience? Okay, stand by.
Hi, Nora Wallace, Santa Barbara News Press. Perhaps this is for Dr. Eisenhart, but anybody could address it. I tried at the previous panel, but I'm looking for, I understand the wow factor of the science in this and why you all are excited about it, but why should someone on the ground, someone that we write for every day, be interested in this mission? What does it mean for their lives?
Sure, I'll take that. Well, when I was a little kid, I used to wonder, how could anybody not be interested in the whole universe? And I think that childlike wonder at what's in the universe is still there in all of us. And so, you know, at the most basic level, we're seeing everything in the universe, and we're really uncovering new panoplies of the universe that haven't been done before. But in terms of more immediate concerns, as Amy described, we're going to learn a lot about the risks associated with the near-Earth object population. Now, that's not to overstate that risk, but it's not a trivial risk either. After all, the dinosaurs, we now believe, were wiped out by a fairly large asteroid, and we still don't know that much about the total numbers or the sizes of the asteroid population. And WISE is really going to tell us a tremendous amount of information about that. And then similarly, I think most people would be interested to know that there are all these nearby stars out there that we haven't yet discovered. And to me, I think that's probably the most exciting discovery that we hope that WISE will make. Of course, we can't guarantee that there will be a brown dwarf closer than any star we now know of, but we can guarantee that there will be lots and lots of nearby stars discovered by WISE that we don't know about now.
All right, any other questions? All right.
Janine Scully, Santa Maria Times and Lompoc Record. How long, or once the hydrogen is gone, and is there any kind of mission left, or is the mission pretty much, from your standpoint, gone at that point?
I can answer that. The hydrogen is essential for operating the long wavelength 2 bands of WISE, but we believe that the short wavelength 2 bands will still operate even after the hydrogen is gone. The interior of WISE will still be very cold, about liquid nitrogen temperature instead of solid hydrogen temperature. And so there is the possibility of a warm mission. So we may, funding permitting, continue operating for 3 months after the hydrogen runs out to complete a second pass around the sky.
All right, any additional questions? All right.
Nora Wallace again. Dr. Eisenhart, I'm not picking on you, but this comes back also from the November press conference, but you talked, and today as well, about the scientific studies conducted from the mission in '83, and you spoke about hundreds of papers every year. What's the expectation for WISE? I mean, are people lined up, scientists lined up, waiting for this data, not just for Christmas? But
They are. We have, because we're observing the whole universe, we actually have a fairly sizable science team. We have 21 members on our science team that study everything from asteroids to distant quasars to the structure of the whole universe. And we've been getting, I would say, several inquiries every day now about somebody wants an early look at the WISE data. Can't we just give them a sneak peek just as it's coming out? And we can't really respond to every request like that because we're actually working very hard to get the data out to everybody as fast as we possibly can. So there's a lot of interest. We've been talking with other all-sky surveys, such as the Planck satellite, which launched earlier this year. We've just concluded some preliminary agreements with them about looking for sources that match up with the Planck survey, and we're exploring similar agreements with other all-sky surveys. So I would say the interest is really quite large, yes.
Another question?
sorry. and I don't know who to address this to, but I wondered, I don't cover the James Webb mission, and I haven't learned so much about it, so I'll apologize from that standpoint. But can it be adjusted at all depending on what WISE finds? Can its mission be retracked?
Take this. The James Webb Space Telescope will be a pointed observatory. So it will only image a small part of the sky, and you need to point it at an interesting field in order to get the optimum results. And so, in fact, sources that WISE finds will be rather high on the list, I expect, of targets that the James Webb Space Telescope's looking at. And so while it's not changing the design of the James Webb Space Telescope before it gets built, it will definitely change the scientific program of the James Webb Telescope once it gets launched.
Okay, another question here in the front.
When should the people who are so eager for the images, when should they expect the first image?
I could answer that. We have a commitment to release images within 1 month of the start of the survey, and so we'll definitely be doing that. And I expect as we uncover particularly spectacular or interesting objects, as we're poring over the data, making sure that it has the quality that we need it to, we'll probably be releasing additional images. But the major image release and catalog release, they'll be in 2 phases. The first one, 6 months after the end of the survey. And as John said, we're expecting that survey to last, the hydrogen to last about 10 months, so that should take us through October. And then 6 months after that, we'll release the first half of the survey data, and that will be out in April of 2011. And then a second and final release will be not quite a year later in March of 2012. Now, that may seem like a long time to reporters, but in fact, for astronomers, this is a frighteningly rapid release because it's just a tremendous amount of data, and we have to get it right. We don't want to be putting out poor quality data. We don't want people to be finding detector defects or little glints from the moon or something like that. We want to be sure that sources in that catalog are reliable and worthy of follow-up with the James Webb or the Keck telescope or other telescopes.
All right. No problem.
Mine. Dr. Mainzer, in November, and also Dr. Eisenhardt, in this press conference, you both talked about mitigation measures for better planning for the unknown asteroids. And I noticed that some of the media coverage after November talked that was what they highlighted. And I wanted to talk to you, are you in on planning for any potential, analysis or campaigns to help the government if something like this were to emerge?
Well, I would say that the best mitigation strategy, if you will, for asteroids that WISE can contribute is prevention. The best thing to do is learn more about the asteroid population. As of today, we know of approximately 6,000 near-Earth objects whose orbits take them close to the Earth. Now, that doesn't mean that they're going to hit the Earth, but it means that their orbits are close enough that we want to pay some attention to them. That's about 6,000 objects, and we estimate, though, that the total population is in the tens of thousands. So we only actually have identified a fairly small fraction of the total population of near-Earth objects out there. So we would like to know more about the population, and that's what WISE is going to teach us. It will tell us about how many there are, what their true size distribution looks like, so how many of what size, how many dark ones are there, how many bright ones are there, and we'll learn something about their compositions. And that's going to help guide future missions should they need to plan an actual mitigation campaign.
All right. Any other questions? All right.
My last question, how eager, we've kind of heard some from someone, but how eager are the rest of you to see this mission and to be this close to it, and then how frustrating is it to see this weather forecast?
Well, I could take a stab at that. We're very eager. We've been, the SDL crew has been servicing this instrument up here at Vandenberg since October 23rd, 24/7, and we're anxious to see it launch successfully, but not so anxious that we want to take risks. We want it successful, and if we need to stick around another few weeks to get the right weather conditions, we're very happy to do so.
And I would add for my part, in terms of excitement, I'm trying hard not to jump up and down right now.
All right, with that, we're going to close out our science briefing today. I'd like to thank our panelists for taking the time to to join us today. And if you'd like further information about the WISE mission, join us on the web at www.nasa.gov/WISE. Look forward to a great launch Friday. You can watch it on NASA TV. Have a great day.